All right, thank you. I'm proud to present our research results here. My name is Eugene, and I work at ERPScan. So in ERPScan, we do a bunch of security research in the field of ERP security and business application security. My role as a head of research and development in ERPScan is to lead a team of security analysts, mathematicians, and developers to run some experiments in the field of security monitoring, threat detection, and actually user behavior analysis. And then later on, our experiments may get into the main project. So the purpose of this talk is to show you how to use machine learning and some other interesting things to solve security problems. So I want to motivate your experimentation rather than to teach you some mathematics of machine learning. And I hope you'll see that it's not rocket science and you can apply it to some tasks at your work or at home. So it's not a security talk about machine learning. So it's a security talk about machine learning, so it's not a machine learning talk about security. And I will simplify some machine learning concepts so we can focus on security. And I also simplify some threat model stuff so it's easier to follow. And another note is that I'm presenting the results of like research projects, so it's not about production, so we don't care about scalability or performance for now. So we work in ERP security, and my presentation will be in this setting. And if you don't know anything about ERP security, it's okay, because most people don't, and that's the problem. If we think about the traditional measures that companies implement to cover to run some security initiatives, it's mostly about infrastructure and not about some business security processes. And big companies like with the dozens of thousands of employees, they most likely have these ERP systems. And ERP system is a business management platform where actually all business processes are happening. So companies control everything they have there, assets, data, and so on. And you can see this is like an example of modules that we have in ERP systems. And you may see that if we compromise sales and distribution modules, we can get some pricing data, and companies may lose some competitive advantage. Or if we compromise financial accounting modules, we can execute some financial transactions that are fraudulent, so we can get some financial profits. And if we break into production planning or plant maintenance systems, we can disrupt some SCADA processes. So it's really a critical system, and it's traditionally overlooked. So that's why it's a great target for cyber criminals. And since all users in these corporations are forced to work inside these SAP systems, it's also a perfect place for user behavior analysis. And I don't even have to provide you any numbers from the breach reports to tell you why the majority of security incidents happen. So you know that it's usually a result of non-patched systems, absence of security monitoring, as well as compromised accounts and malicious insiders themselves. So cybercriminals can use spear phishing or social engineering to hijack user accounts, or simply bribe insiders so they perform some deliberately malicious activities. So users are the main and easiest attack vector nowadays. So that's why we need to shift our security analytics from infrastructure to users. And at this moment, I don't mean any advanced analytics, machine learning stuff, rule-based systems, whatever. I just want to emphasize the difference between perimeter security and user security. So if you work in security monitoring, you most likely get more security alerts that you can investigate. And if this is the case, most likely it means that you don't have a mature security model in place and some meaningful use cases. And some vendors that claim their advanced analytics may not be the hype, but really helpful solutions that help you with these threat models and use cases. So they usually have some built-in scenarios for detection. In case of UBA, it's user-related use cases. In case of network security, it may be network-related use cases. So my piece of advice is to consider these tools like extra level of analytics on top of your CM system, and CM would play a log management role, not a security analytics role. So your main goal for security monitoring must be creating a meaningful threat model, then designing some useful use cases, and finally find the solutions for these use cases. So you don't look at CM alerts, but you look at like this analytics solution alerts. This like additional filter. And another point about traditional security monitoring is that it's usually security focused, and it's rarely enriched by business data. Like when we have a lot of information about servers, different applications, then we can find that we can correlate it with our alerts, and we can prioritize some alerts for more important systems. And for UBA, there are a lot of systems like HR systems, CRM, Active Directories, and so on, that give us a lot of useful details to build some meaningful user behavior context. And the final thing I want to mention about UBA is that it's not the same as fraud analysis, because UBA is mostly about facts in a technical context, and fraud is about some malicious intentions in a business context. So to build user behavior analytics solution, we need to create a user-focused threat model, then define the most important use cases, or we can call it threat scenarios. Then we need to identify data sources, including non-security data like CRM or HR systems, and we build the user baseline, the user behavior context from these data sources, and finally we monitor deviations from the baseline. And talking about machine learning, you know that most attacks nowadays are almost fully automated, and it's not longer a manual work for cyber criminals. And large-scale attacks have been automated for years, and I'm not even saying about like machine learning weaponizing. So it's not longer efficient for humans to create rules and signatures, because we'll only respond to attacks after it happens, not before. And the main goal for defensive security must be to learn what is good and detect some unknown attacks. So we still need a lot of human expertise in these machine learning driven solutions, and I will show a lot of examples about this later on. But anyway, it's obvious that machine learning stuff can help us to build some self-adjusted dynamic behavior patterns. So we can get some behavior profiles of networks, servers, devices, and so on. And one of the greatest things about machine learning is that it can help us to extract some knowledge from the data which is not visible to those people who create signatures and rules. So what is machine learning exactly? First of all, it's not rocket science, or it's not magic. In fundamental research, machine learning is about mathematics, but in applied research, it's mostly an engineering problem. So from the mathematical point of view, most problems like clustering, classification, regressions, it's they already solved. So it means that given the right data, right parameters and time, these problems will be solved with good accuracy. So our task would be to create or transform the data suitable for the algorithm and find the right parameters for this algorithm. So machine learning algorithms are based on approximation idea, so it helps us to learn from the data and use this knowledge and apply it to the new data that the algorithms never seen. So we train the algorithm by providing the data, and depending on the task, we can use different types of learning, which you can see here. And training is actually an automated process, and to security people, I like saying that building the machine learning model means that you just need to do some engineering and then brute forcing the suitable parameters for the best accuracy. And so building machine learning model means that so the model is a kind of the solution, the snapshot of all the trained algorithm and its environment and the feature encoding capabilities. So it's not difficult to get the very first results with the average or so quality, and the most time you'll spend on tuning the model rather than just developing it. And it basically makes up to 80% of any data science project, preparing the data and tuning the metrics. So preparing the data means that we need to extract some features and encode them so we can feed it to the algorithm. And features are basically facts about our data entries. Our goal is to find the best features in our data, and that's why we need a human expertise in our case in security to find these things. There are various types of features we can extract from data. These features can be raw, derived, and for log entries, like we are talking about security monitoring, it may be some facts like time, action, program names, or it may be some observations based on your analytics. So this is why machine learning driven solutions is hard to build, because it requires human expertise in the domain, like in our case security domain. It requires machine learning expertise to build and tune the model, and finally it also requires the right product and the right business problem to apply it to. So this is a generic life cycle of machine learning based security solution, and instead of anomaly detection box, it could be like malware detection or web application vulnerabilities detection. And my presentation will follow this workflow with some minor changes, and I will cover the top 4 boxes and anomaly detection box. So first of all, we need to prepare the data, and as we are talking about security monitoring, the first thing we need to do is to collect relevant data. There are usually dozens of sources in enterprises, so you may want to build a spreadsheet of all what systems you want to analyze, what kind of logs do they store, and all information which is available and which you want to get. So if you're lucky, you'll find that some network operation centers or any other security monitoring guys have done all the stuff already, so you just have a single source with all the data unified. And if you're unlucky, you'll spend probably most time on this data preparation rather than building the machine learning model. So if you're unlucky, you'll have to understand a lot of different formats, log formats across all identified systems. So there are many options. Many of them, I would say almost all of them are terrible. All of them are terrible. That's easier to say, and this is actually true. So there are many formats, some documented, some undocumented, unified, not unified. The thing is that you'll work with the sources from every example from this list, and it's really a mess. So you just don't give up. It will end sometime soon. So that's okay. Then to normalize data, you need to understand all the pieces of information you have in these logs. And for user behavior analysis, you must know when, who did what, where from, where to, and on what asset. Then all these fields must be identified across all log formats. You must unify the fields, and actually there are several options. So you can see that these are the scenarios. You can build a special tool which will sit outside of the module. You can build it as a built-in converter, and you can use some infrastructure for this task. So actually it depends, depending on scenario, you or other guys will do it. You can outsource it to monitoring guys, for example. And finally, you must check if there are any duplicates or missing fields in the data. For duplicates, the most common scenario is when one action generates several options, like when the user signs in and actually provides just passwords and presses enter, like several events are generated, like the user login, the password check, and so on. So we may want to prioritize them and maybe exclude them from the analysis. And for missing fields, the most common scenario is when a web server doesn't identify itself in the log files. So basically, after you collect several log files from different servers, you don't know, looking at the logs, where you get this log from. So during the normalization and enriching these log files, you need to add some missing fields. So for the sake of this presentation, I will only demonstrate this with just one log file, which is the most relevant and rich with data. This is the example of the SAP security audit log file from a web platform, and this is actually what you see in the log file. So this is just one log, so this is just one line. There are no log entries here. Log lines, just one line. Every 200 bytes is the new log entry. So this is the mess. We had to understand this, and later I'll show you that there are around 50 log formats in SAP, and most of them look similar to this. So we spent many weeks to understand and to normalize and to convert all this data to unified format. So here we have 5 events. This is the before and this is the after. So these are exactly the same events with some less important fields missing. So at this moment, if we went through all the steps for every log source that we have, we may have good enough data sets. And now it's time for security analytics. Business applications usually collect information about internal processes for user activity analysis and for some debug reasons. So these pieces of information provide some valuable context-related information. And this is what almost every application will have in their log files. So if you find the log files without this data, probably it's not log file or some random stuff. So ERP systems are very complex, and they have several platforms with dozens of modules and hundreds of business applications. And this is a crazy combination because some applications dated back to like 20 years ago, or maybe they're older than me. Some applications have been acquired from other companies, and they also have new developments. So obviously there is no unified security login mechanisms, no unified formats or name conventions. So we have identified over 50 types of information in the fields across all components in SAP systems. This is the short list of what we want to look at today. So this will help us to analyze various types of user anomalies. We can build multiple models for user behavior analysis and discover different scenarios. So you don't have to put all your data features into one model. You can split scenarios by models and by algorithms. So for this presentation, I will just use a small set of features so we can focus on the process rather than on this data mess. So now we need to build a threat model and use cases for our solution. So we have designed a threat matrix with categories, classes, and scenarios. And the idea is that categories tell us why we want to detect it. Then classes tell us what exactly is going to happen. And scenarios tell us what we need to look for in the log files. So now we have a threat model, and I will show you a spreadsheet a bit later. So I have the threat model, and we can see what we need to detect, and we need to link it to the data sources. So we can build a spreadsheet and check what kind of information is missing, or like, are you ready to catch these scenarios? So this threat model is helpful for many things. You can collect data and craft your data sets according to these scenarios. You can prioritize some scores and alerts, and you also can assemble these cases back with some classification rules on the post-analysis stage. And this is, let's start with the security data science. We actually, in the big teams, when you have like security data science initiatives, there are always guys who are more competent in security and more competent in machine learning. And we have some rule of thumb that machine learning is kind of work that happens after the vector is created, and data science is everything from threat modeling up to the data feature engineering. So data science is kind of security plus some algorithms. So for anomaly detection, it's actually a popular application of machine learning as much as classification or clustering. And from the scientific point of view, there must be more types of anomalies, but today I want to focus on this. Static anomalies are those that you may use for clustering or classification, and it's basically about the log entries and key value pairs from your data. The traditional example of static anomalies is that the user has a new device, a new IP address, the user connects to a new server, and so on. So they're static because we analyze them individually, so historical events don't contribute to the analysis of the new event directly. It just means that the historical events build the context of the user. And temporal anomalies are those dynamic things you may see on the timeline dashboards. It's like the unusual time, unusual volume, event sequences, and so on. So the problem with the anomaly detection we need to solve is that most anomalies are deviations from the mathematical point of view, but they're not malicious. So we need to do something with this. This is obvious because huge infrastructures are evolving and changing, and some anomalies kind of normal, so they're not security risk. For example, wrongly configured system may send a lot of log messages, and some monitor mechanisms may think that this is kind of spike in activity. So to fill this semantic gap, we need to combine some machine learning detections with the actually security analytics, and that's where we can use our threat model. So my vision was that we need to create a threat model, extract some behavioral characteristics, and then map those characteristics to the machine learning algorithms. So we can see that if this is relevant at all to use anything to detect these cases. So this is a very simplified example, so it doesn't make sense to copy and paste these results. This is just an example. So what you want to see in your matrix is the big number of highs and mediums, which means that the columns are what we can detect with the algorithms, and the lines are what we want to detect. So if we see many lows, it means that it doesn't make sense to, it means that we cannot detect this scenario with the existing tools. So we rather need to redesign our threat model or find some other technical ways to detect this. So I will show one approach for static anomalies and another approach for temporal anomalies. So I will show them separately, but in production you want to see like many models, many approaches under one umbrella. So let's start with the static anomaly detection. Static anomaly detection employs the idea of behavioral whitelisting. It basically means that we collect all information about all user parameters from the historical activity, and then we match that data, the new data, with the historical context. It also may be useful for explanation of machine learning models, like when you have this very simple, predictable, and understandable results linked to some event ID, you may use to explain another alerts from machine learning algorithms that doesn't explain why the alert was triggered. So you can correlate it by event IDs. So behavioral analysis requires that we know what is normal for a user. So we need to build a historical user context. So it's all information ever paired in the log files. So basically, as we have seen in the data formats, we may have a key value format, and for every key you collect all the values from the historical context, such as previously used servers, applications, and so on. The obvious problem is that during the training, during the learn stage, we don't know what is normal, so we don't actually analyze, we don't look for anomalies. We think that we know that nothing happened, there were no incidents, and we assume that this data set is normal, so it has no anomalies. So it's possible to call some anomalies normal, and then in the future this user, the alert won't be triggered. So to recognize those potential anomalies during the training step, we use a frequency analysis of the waitlist features. So it helps to discover the rarest features and exclude them from the user context. In the first table, you can see 3 waitlisted IP addresses, and actually before we finish the training step, we need to exclude this because it's obviously not normal. To do this, we have a mean threshold, which is 219, and it obviously cuts off this third IP address. But if attackers know our algorithm, they can simply bypass our threshold by injecting more entries. So in the second table, you can see that after the third entry, I added 20 more entries, and the threshold is changed. So it's now 28, and our anomaly becomes normal. So that's why we need another kind of threshold. So for importance amplification, we use the threshold, which is like simply mean of squared values, and it's simple but efficient. And the same threshold we can use for analysis of the alerts, actually in analysis stage, because sometimes it's possible that you didn't get enough data to cover all scenarios, or like the data set that you have for a specific user isn't relevant because in this month the user was in vacation and later he changed his job. So in this case we can find many anomalies that happen regularly, which means it's not actually an anomaly, and we can use this threshold later on for kind of whitelisting those reported anomalies. And finally, the anomaly detection itself is based on context matching. So when a new event happens, it must pass through some matching checks. So it means we compare every new event with the user context field by field. Like we have the new event with this IP address, and we check does the user has this IP address in the list of whitelisted IP addresses. So it's pretty simple but efficient, and every mismatched field gets an error score. So similarly to threat model, we have a kind of table with all the event types, event fields, and weights. Like the weight may be 1, 2, 5, 10, depending on how high or low it would be. And if the user has two anomalies in IP address and in a server, like he never used this IP address for his device and he never connected the server, it means that we have two anomalies, and the total event anomaly score would be the combination of these two. And then for actually analysis, we prioritize users for investigation by a total user anomaly score, which combines all events of this user for a specific time frame. Like users are prioritized by the total user anomaly score for the day, for the week, for the month, or whatever. So this is the simple idea of static anomaly analysis. And for temporal anomalies, we can use a more advanced approach. So basically, to detect temporal anomalies, we need to establish a normal behavior baseline with the different means. We need to train our algorithm to predict normal user actions and actually analyze and correctly predicted actions. So first of all, we need to start with the feature engineering, which includes feature selection and feature encoding. As I mentioned, we have security audit log, and this is the example. So let's take a look at this and see what defines the action. Well, obviously, the time is needed to understand the dynamics and the order of the events. The action is needed to understand what is actually happening, and some context may help us to see what the context of the action, like the program name, the table, and so on. So in our model, we want to predict a user action, and these are the fields that may be useful for this model. We can build many other models that use other data fields, like we can build models for account sharing, so we'll focus more on devices and servers rather than actions, for example. So these green things that I highlighted are actually features, and the group of features combined together is called a vector. So vector is a mathematical representation of our features in the form of matrix. So in this case, we have 1/3 matrix, and this is sent to machine learning algorithm. And as far as it's about mathematics, and each feature would be a dimension, so we have 3 dimensions, and the feature value is a position in this dimension. So in order to convert any event into a vector, we need to know all possible values. And as we work in ERP context, we must know that ERP ecosystem is kind of closed but very advanced, and SAP platform is like a, I would say, operating system with its own group of transactions, applications, reports, and so on. So if for a transaction start, we need to know some possible transaction names. For table read, we need to know the possible names of table names. This sounds crazy that we need to know all this stuff, but actually if we detect anomalies in the core system, which is actually 95% of any ERP installation, this is totally okay. So to know these names of programs, we need to create some kind of knowledge base where we keep all possible names for transactions, reports, and so on. So there are several options for our knowledge base. It's possible that we would have more options of knowledge base if we have different type of data. But in this case, the on-the-fly knowledge base means that actually we don't have a knowledge base, and the way it works is we collect all names of programs at the start of our model. The obvious problem is that we don't have, so we only work with the data that existed at the moment of feature encoding. Another example of knowledge base is security focused, which means that which implies some security analysis. In this case, we can focus on the most critical transactions and tables, and this lists of critical transactions and tables and so on, other entities, it's common knowledge. The problem is that what is critical for you might not be critical for another company. And the other problem is that to see what is critical, you need to go through all the list of possible names. So this scenario doesn't scale. In our case, we have around 500,000 options of names. These are like the standard built-in options, and we only focus on these built-in options. And finally, the application-focused knowledge base means that we just extract all the names from the application itself. It must be documented, and it must be able to be extracted from the system itself. It sounds inconvenient, but in our case, it's the only way we can scale our solution and avoid any manual review and analysis. So in this case, we simply have a list. It's not a list, but in simple words, we have a list of all program names, and then we just have 500,000 list, which we need to convert to vector. The problem with this is that we have like 500,000 options, and every option is assigned a feature value. But in fact, company might have only, or dataset might have only like 500 names or 1,000 names, but not 500,000 names. So we'll get some random chunks of points in the space in different areas, which doesn't make much sense. and with the mapping, we can like do some reduction of the scale. So we assign feature values from the range, not from the range of 500,000 options, but from the range of like maybe 1,000 of options. The idea is that every transaction or every program delivered to ERP system belongs to some software component, which means that this software component brings a bunch of programs created for some one function. For example, when we have like 10 programs for payment processing, like receive payment, send payment, check payment, whatever, then we can just group it to some payment group. And with the mapping, when we see the payment program in the log files, we assign, we kind of see what groups this event belongs to, and we assign the feature value according to this grouping, not according to the original list of 500,000 programs. And finally, the machine learning stuff. As I mentioned, we consider that machine learning starts when their feature vectors are ready. So in this case, we need to find the right algorithm for the task. We need to implement the model and its environment, like feature encoding and all the stuff. And finally, we need to optimize our model for the best accuracy. In our case, we want to analyze user activity, temporal anomalies, which implies that we have some kind of timeline, some dynamics. So for this case, we need an algorithm that can build some context and maintain some kind of memory. And this makes us use recurrent neural networks that have like feedback loop in the recurrent layer. And these feedback loops enable us to accumulate information over time. And that's why RNNs are a traditional choice for time series analysis. The problem with RNNs might be that it's harder to approximate some longer dependencies, and the more difficult for analysis dataset you have, most likely that you need some more advanced options. So you can see the list of more advanced options here. So long short-term memory, or LSTM, is the most popular option, and it's actually have a huge history of successful implementations in tasks similar to this. There are also papers that compare LSTM to RNN and other options, and we can see that on simple tasks it may be a little bit overkill for the task, but the more complicated data we have, the more useful LSTM might be. So LSTM has memory cells that maintain information. So actually the top line, you can see that which goes through all the cells is kind of memory, and the bottom line is kind of reactions. In fact, this is just one cell. It just shows that this cell returned the result to itself. And this is how the memory works. So this was our choice. And in fact, this is the architecture of our model. As input, we have our feature vectors for time, for actions, and for program names. Then we have a layer of LSTMs. Actually, these are LSTM cells with the multiple neurons inside the cells. And for every LSTM cell, the separate piece of vector is sent. So for time LSTM, we have, for example, maybe 16 neurons because we don't need huge memory for the time prediction. But for actions and for programs, as we have huge knowledge bases, we need some more memory. So in this case, we have like maybe 200 something neurons in these LSTM cells. And as we can see here, like the output of the LSTM cell is kind of reaction, and in our case, this is the reaction of like 16 neurons or 256 neurons, and this all these reactions are sent to the final output layer that combines all this information and returns a single value. And this single value is a prediction. Like after this three events, what would be the fourth event? So when we build this model, we have a bunch of parameters that we can tune. Like these parameters are relevant to architecture. They also called hyperparameters. So these are global parameters that define a high-level behavior of a neural network. The data parameters is about how we cook our data, and finally, training parameters are about how we see the results and how we tune the accuracy, like thresholds, smoothing, or other things. So finding the best options for these parameters, partly an engineering task. So, like, you just need to try several options and see what works the best. So I want to show you what we found the most useful things, and they're mostly related to data rather than to some machine learning native parameters like architecture. So first of all, as we detect user actions, we want to look at sequences of events. As far as machine learning task is to find patterns in data, we want to find what the best length of the pattern would be. So the idea behind it is that users perform the same actions the similar ways, and we can easily track these sequences. For example, if a user wants to send a payment to a contractor, they need to first authenticate, then to run a finance program, then 3 to find a contractor from the list, and 4 we need to send a payment to the bank. So this is the 4-step process. And after we collect these scenarios from many users, we can ensure this that after 3 events, the known fourth event happens. So we kind of predict what is supposed to be next. And obviously for the long sequences, it may be harder to find the sequence length, but it doesn't mean that long sequences are bad. There are many types of users. So actually there are three main types of users. It's regular business users, like privileged users, like system administrators, who may occasionally run some multiple actions, and there are service accounts that are actually automated or scripted accounts, and they may have like thousands or tens of thousands of events per day, and we also want to find anomalies in their behavior, because one of the most common attack vectors is that you have a bunch of standard users with the default passwords, and they are used in production, but passwords are not changed. So the human may sign in with this account and perform some activity. So we must find anomalies in sequences, maybe of dozens or hundreds. events. So that's why you need to get the right sequence length for a task. The next thing is about knowledge base. As far as our feature vectors are points in the space, we need to organize them, kind of group them in the space, because it's very critical for us as we define the anomalous events based on distances in the dimension. So our threshold is distance based. And in our case, we had several options how we organize our knowledge base. We can organize it by alphabet, by criticality, which is actually a security related thing, and by frequency. So alphanumeric way doesn't make sense because it doesn't place programs together based on their importance or criticality or business value. And users actually run a bunch of programs. And I don't think that one group of users will only run programs starting with A, and another group of users starts programs starting with B. So for prediction reasons, all these points will appear in the random areas. And you can see that it didn't work well on the first picture. The criticality, sorting by criticality, means that we need to prioritize the most business critical transactions or programs. But we dropped this idea because it requires to go through all the 500,000 options and prioritize them, which doesn't make sense. And frequency is the most suitable way for us, because we can see that most common events will appear close to each other in the space, and we'll see less deviations here. And the reason it's important for us is that we define our threshold and anomaly of the event by the distances. So our model output is not a binary answer like it's anomaly or it's not anomaly. Instead, we have an error score, which basically a distance between what was predicted and what actually happened. And if predicted value is like 0.6 and the actual value is 0.8, we have 0.2 distance. So we call it an error score. And then this error score is compared to a threshold. So there are several options how we can define threshold. You can make it adaptive, you can hard-code it and report every all top 5% of the most anomalous events and so on. The problem with this is that if you don't have anomalies, you'll still report the top 5 results, which are less normal than others. So in our case, we have adaptive threshold. The way we get it is that during the training and validation, we learn from the data, and then we try to predict the same data set again. So finally, assuming that all the data set is normal and we don't have anomalies there, we get the biggest error, the biggest distance as a threshold, which means that if everything is normal, even if there are some like deviations, then what is more than this deviation would be anomalous. And we can change the sensitivity of this threshold by multiplying it with some coefficient. So you can make it stronger or make it weaker. And here you can see the distances. So the green things are the distances between this stuff. So finally, for anomaly detection, what we do is we predict a potential user activity and report incorrectly predicted events that are above the threshold. So in this case, you can see the prediction timelines for time and actions. And the blue line is what we have predicted. and the green line is what happened actually. So you can see that the blue line looks kind of normal in case of time, and we have a huge spike, green spike, of what actually happened, and that's why it was reported as anomaly, which you can see in the middle as the red stars. And with the action we actually see the same. So we can see that the green lines and blue lines are not exactly the same, but the distance the distance between these blue dots and green dots is less than threshold. That's why they're not reported. We use this. We actually labeled our data set with anomalies, but we didn't show these labels to our model. So we only use these labels for visualization and for analysis of the results. So this red signs at the bottom are anomalies that we put in our database, and the red stars is what we actually detected. And you can see that most things that we labeled in our data set are detected by the algorithm. So this is the final metrics of our experiment. So we managed to get accuracy of 95%, which means that we have a data set and labeled some events, and to have two groups of things. The first group is what we need to detect, and the second group is what we shouldn't detect because this is safe. So from the security anomalies we have found 71%, and from the things that we shouldn't detect because they're safe, we called as safe 97% of results, which means that the rest 3% is false positive. So we don't have anomaly, but we reported there. And false negatives are those anomalies that we put in our data set, but our model didn't actually find them. And this is easy to explain, and it doesn't mean that this is bad. The idea is that we put anomalies in our data set according to our security knowledge, and many our labels are anomalous from the security point of view, but they're not anomalous from the mathematical point of view. And on the other hand, some things that we think are safe, they were reported by the algorithm because they were mathematical deviations, even if we think that this stuff is normal. So finally, as a conclusion, I want to say that as you can see, the machine learning stuff is not rocket science, and one of the most difficult things is about data and security analytics. So in our case, security analytics has more importance in the project than the machine learning itself. Then another conclusion is that machine learning driven solutions may be very useful, but they must help analysts to prioritize the alerts and to find some things for investigation rather than to replace those analysts. Then another conclusion is that we need to adjust accuracy and tolerance to false positive to a specific situation in a company. It's very similar to a traditional fight between security and usability. So in this case, you also need to find some balance. And finally, there is no any algorithm that solves it all. So we need to build a bunch of algorithms. We need to run many experiments, create many models, and put it all under one umbrella, so you can help each other to detect the right things. So that's it. Thank you.
Thank you, Eugene. Any questions for Eugene Neyolov? Oh, there we go.
Just wonder, you mentioned you used the RNN algorithm for machine learning, in the machine learning algorithm for your cases. So just, I wonder why you choose, your company choose that algorithm for machine learning. Is there other use cases using different machine learning algorithm?
Yeah, so we use LSTM as the most universal solution because I'm showing you the example with some simple task, but actually we have much more complicated dependencies in the data. We have correlations between multiple logs, and we started with this algorithm as their most universal solution, and with the idea that once we know how it works, with the one case, we can apply this knowledge in other cases, so kind of transfer learning for humans. But yeah, I agree that there are many other algorithms, and definitely will try many of them because my department is responsible for experiments, not for production implementation. So if you're curious, you can sign up for the blog and follow our machine learning posts. Thank you.
Any further questions? No? Thank you, Eugene. Please give him an applause. Thanks.